Dear friends, welcome to this Electrical Engineering Knowledge Sharing channel, AMP Power System Workshop. We are discussing session 11, Switchgear protection. We have already completed two parts. Today we are continuing the rest part of the busbar protection, that is under part 3. In the part 3, we will be discussing, in part 2, we have already discussed your busbar protection, that is over current scheme we have discussed, partial differential scheme we have discussed, and conventional circulating current, low impedance circulating current principle also we have discussed. Now today we will be continuing continuing this scheme, and we will be discussing another two scheme, that is your low impedance bias differential scheme and high impedance voltage differential scheme. Now, when we were discussing in the part 2 about conventional low impedance circulating current principle, we have seen that this scheme can be applied to a non-critical 15 kV and onward switchboard with a limited number of feeders. We can apply this circulating current principle, which operates on the Kirchhoff current law. In that scheme, the relay which we use, it is a normal conventional differential relay. The relay has a pickup setting, so we put the pickup setting. Then the moment the pickup relay receives from the CT the pickup current, then on the pickup current it will operate instantly. So if you see the characteristics of this relay, the relay characteristics will be like this for the normal conventional circulating current differential relay. If this side, if we represent this, suppose this is our differential scheme we have already shown. So this is a 2CT, this is a busbar inside, and here we have connected the relay in this way. This is our relay. It is one phase way I am showing you, 87 bus differential relay. So this relay, how it will work? So this current, suppose this is a primary current I1, and this is current, suppose I2. Normally, normal condition, both currents are equal. Suppose this is a current I1 and this is a current I2. This is the secondary current. So if we plot the curve in terms of secondary current, and the relay current will be how much? I1 difference I2. That is the relay current between these two currents. That is called spill current, or I delta, or differential current equal to I1 difference I2, which will be better, modulus value of this. Now this side we are putting this, suppose this is a fault current IF, this equal to I1 plus I2 by 2, average of this, and this side we are drawing that I differential, that is a I1 minus I2. If this is the way, then this suppose the pickup setting is 10%, suppose this is a 10% setting. That means, what does it mean? When the spill current, difference between this I1 and I2, the current flowing between these two sides, this city and this city, if the difference of current I1, I2 is 10% of IF. Suppose if I give the pickup setting 10%, it means when this ID equals to 10%, means 0.1 of IF, this IF, immediately the 87B relay will operate. And the moment it is operate, then it will be operating this way. That means this is the current, this is the fault current, okay, IF. So normal load condition, it is, if this relay need to operate, at least 10% differential current should flow through the relay, then only the relay will operate. So when the normal healthy condition, both currents are equal, so differential current will be 0, so it will not operate. But the moment there is the internal fault, then I1 minus I2 will be 0, I1 will be equal to I1. So there will be fault current will be there, immediately fault current will be the full value, immediately the relay will become and it is operate. Now problem with this relay, this 10% pickup setting which we have given, this is the for any fault current, yeah, this is instantly it is operating. For any fault current, this relay is operating. Any other fault, there is no change of the characteristics. This is a straight line parallel characteristics. Now issue with this, in the differential protection, for the busbar protection, we have seen so many cities are there. If there is a 4 outgoing feeder has a 4 cities, then incomer cities there, bus coupler cities there. If we consider two section of busbar, if we consider the switchgear is like this type of switchgear with the 2 incomer and bus coupler, and all the outgoing is going from here. Suppose each section has a 4 outgoing feeder. In that case, there is one city over here, one city, each feeder has a city, so there are more number of cities. And we said that all the city, though we are taking all the city identical ratio, but during manufacturing of the city, though the ratio is same, but the characteristics, magnetization characteristics will not be equal, burden will not be equal. So there will be mismatch. And due to the mismatch, what will happen? The city transferring secondary current will not be always equal, though both the city are identical ratio. So there will be always some spill current is there, and if this spill current is more than the peak of setting, immediately during healthy condition also the relay can operate. That is one point. Second point, if any of the city during external fault, suppose the fault is that day we discussed, if the fault is over here, then all this fault current, suppose this breaker is closed, fault current will be coming this way, and this city will be carrying the entire fault current. So this city may get saturated. If this city gets saturated, then automatically this city will not give any output current. Automatically the differential scheme which we joined all the cities together, that will give a differential current. Immediately this relay will operate for external faults. So this 87B conventional circulating current principal low impedance relay is vulnerable and it is not very reliable. It can operate at any instant if there is this type of situation takes place. So this is the disadvantage of this normal circulating current principal low impedance relay. To overcome this problem, what we do, we can improve this low impedance differential scheme using a bias characteristics. So how these bias characteristics help us? That is we can explain this thing. We have discussed during the generator protection voltage resistant overcurrent relay, 51V relay. We have seen that voltage resistant overcurrent relay, when the voltage is healthy, 100% voltage is present. Suppose the relay operating on the current of 100% current, 100% of I current. Suppose this is the current required to operate at 100% voltage. The moment this voltage drop down to 80%, automatically current required may be 70% to operate the relay. When voltage come to 50%, maybe current required only 40%. So this is a voltage resistant overcurrent relay is operating in this way. So when this, that means the operating current is not fixed. In the case of normal conventional differential relay, which is just shown in the previous characteristics, the operating current is constant. But if we can provide this type of bias characteristics or restraint characteristics, where operating current will be dependent on the fault current. Here operating current, in the case of 51V relay, operating current is dependent on the voltage. So in the case of differential bias, busbar differential protection, if the relay operating current ID, which was shown equal to I1 minus I2 modulus value, if this ID value we can make dependent on this fault current IF, that is equal to I1 plus I2 by 2. If we can make these are two interrelated, that means the differential, the moment fault current increases, differential current also, relay operating characteristic will be moves up. If we can make this type of arrangement, then we can make this relay susceptible. It will not be susceptible to this C2 mismatch or the C2 saturation. It will be better than the normal conventional relay. So when we include these restraint characteristics inside the differential relay, we call this percentage biased or percentage restraint differential protection or differential circulating current scheme. So this scheme which we apply, that is called, it is still low impedance scheme. Relay is a low impedance type, but the relay has a characteristics bias inbuilt with the bias characteristics. So there is another in addition to normal peak of setting, there is another setting available with the relay which is called bias characteristics, and we can put the bias as per our requirement. So if you see the characteristics of that relay, how that bias characteristics, differential relay characteristics. Let's see the characteristics of the relay. So in the same way, bias characteristics will how we do it. This way we are. So our scheme is same. This is our busbar. This is a busbar. CT is over here. This is incoming side. This is a busbar differential relay located over here. Yeah, 87B. Yeah, this is the scheme. And the current following primary current is I1. This is I2. Corresponding secondary current I1. This is a secondary current I2, and differential current I1 minus I2, that equal to D. Okay. So in this case, this characteristics how it would be. Suppose this way we are drawing I fault current, that equal to I1 plus I2 by 2. Okay. That is average current. And this way we are drawing the ID current, differential current, which can pass through the relay between the, that is a, it is a, we are showing only 2 CT. If it is a multiple CT, all the current we are yesterday on the conventional current scheme we have seen that all the secondary, all the feeder CT will be connected together, and all the primary side, all the incomer side CT will be connected together. This will be primary incoming current sum and this will be outgoing current sum, and that difference is I1 minus I2. In case of single CT we are showing like this, but this is actually multiple number of CT, and we have seen how the CT to be shorted, how the CT summation will be done. It will be, all will be shorted this way, and this sum will be coming as a I2. Here is coming as a I2, and here as it can be 2 or 3 incomer. So all the 3 incomer CT will be shorted. It is one phase I am showing. This will be shorted, this will be shorted, and then this total will be coming as a I1. So this is the way it has been. So this characteristic in the case of conventional CT low impedance circulating current principle which we have drawn, this is a I setting current. This is we call pickup current or I setting. This is IS current. Now this relay, when we incorporate the bias characteristics, what we said, the operating current of the relay, the current at which the relay will operate, in the case of conventional overcurrent scheme, conventional differential scheme, relay will operate based on this IS current. But when we include the bias characteristics in the relay, bias characteristics or restraint characteristics, then the relay will not follow this curve. Then what will happen? From depending on the bias, the relay will follow this type of characteristics. This will be the relay characteristics in the case of, it is in the case of bias. So what we are doing here we can see this is a restraint zone. This area we call is a restraint zone. In this area, relay will not operate. It will be restrained, and this is the operating zone. And this is your borderline, because this is the operating zone. Now what is happening over here? Suppose now the fault current, there is no fault current. This is a zero fault current. It is a normal load current is following. At that time, if the relay need to operate, you need at least IS current. So that IS current, if the CT mismatch, all this thing, if you get IS current, then it will operate. Otherwise, it will not operate. The moment there is a fault or there is a fault outside or CT mismatch is happening in like such a way that I1, I2 are not equal, there is a differential current, then that differential current above this, when the current is here, you need this amount of differential current to operate the relay. The moment the fault current is increasing, immediately differential relay, to operate the relay, you need this amount of current. So as this fault current increasing, you need more and more differential current to operate the relay. So in that case, relay operation will be sluggish. Okay, the relay characteristic or relay operation will be sluggish, but relay will be susceptible relay will not be susceptible to the CT saturation or less susceptible to the CC saturation or CT mismatch. But due to mismatch, suppose when the current is this amount, at that time if this CT mismatch is there, still at that time CT relay operate this amount of extra current is needs. This is the extra current for the from the conventional relay. This relay needs this amount of extra current to operate. So it will give us some sort of comfort to the operation of the relay. Relay will not operate under this mismatch condition. But when there is a genuine fault, immediately relay will operate. So this is called the bias characteristics. So in the bias characteristics to operate the relay, what is the relay current required? That is, we can derive from these characteristics. This characteristics is called bias. The character, you see, this relay has make a angle with this on this fault axis. That angle is called theta. So if we call theta, suppose there is a one section I am taking over here. Suppose this is a, at this point, this is a, suppose the fault current is here. This is a IF1. At this fault current, if the relay need to operate, relay need this amount of I operating current. That is a relay operating current. I can say IR. That is a relay operating current. So what is the relay operating current? Relay operating current equal to IR, relay operating current. This equal to how much? This is IS, relay setting current, plus this amount current. So if this is the value of fault current IF, I can say this is IF1. If this angle is theta, then tan theta equals to how much? Tan theta equal to this amount, suppose H. Yeah? H by how much? This amount IF1. This is, that means the H is equal to what? H equal, this tan theta we call B, is called bias factor. The gradient of this line we call bias factor. So that means H equals to IF1 into B. So that means in that case B into IF1. That means at this point what are the fault current? So whenever we go over here, at this point there is a fault current, so in that fault current it will be there. So if this IF1, if I terminologize as a simple IF, then the IR equals to how much? IF equal to basic pickup current plus bias factor, means gradient of the bias curve into the fault current. That will be the relay pickup current. Okay. So this IS is normally very less. So if we neglect this IS, then B equals, if we neglect this is a very small value, then B value bias factor equal to relay current by IF current. So from here we can see, if we give the more and more bias, as the bias will be more and more, the relay need more and more operating current to operate at the particular fault current. If we change the bias, as we give the bias more and more, relay will need more and more current to operate. That is also clear from the this curve. So as you decrease the bias, it needs less and less operating current. So by changing the bias of the relay, we can change the relay characteristics, and we can make the relay sluggish to operate on the spill current or on the CT saturation condition. So this type of relay, when we use this scheme, we call it bias differential scheme, circulating current principle, low impedance scheme. So this value, the bias now, so if we draw the diagram, this circuit diagram of this, it will be similar to this which we draw for this conventional differential scheme. So we can discuss in this, I think we can discuss at the end of this, the wiring diagram for the CT and the DC scheme for all the three schemes more or less same. Some differences there. Only difference here, all the relay has a different type. That is the main issue. In the normal conventional relay, there is no bias characteristics. In the bias differential relay, there is a bias characteristics. But still the bias characteristic relay completely CT mismatch or CT saturation cannot be, if CT saturation takes place, this bias differential relay may also operate. Okay. To avoid this totally, the CT mismatch, due to CT mismatch, if the relay we do not want to operate, and if all the CT ratio mismatch, if we do not want to operate, then there is a new scheme comes which is called high impedance voltage differential scheme or high impedance circulating current differential scheme. If we make this differential scheme, if you can see, we can make one small analysis why the CT saturation takes place. From there we can make out how the relay can be made high impedance, why high impedance relay will be more will not be susceptible to the CT mismatch or CT saturation case. So to draw this thing, we have discussed this thing during our differential protection, but still on time, another time I am explaining this thing. In case of differential protection, we have seen this is the busbar we have over here, and this is our CT. Okay, this CT. Now if you draw the equivalent, and then it is connected by the leads, and relay is connected over here, 87 relay, differential relay. Now if you draw the equivalent circuit, suppose one of the CTs completely gets saturated. What does it mean? Saturated means this CT, normally any CT equivalent circuit, this CT has a magnetic reactance and then it has a resistance. We know resistance and inductance working in perpendicular. If this is the direction of resistance, then this will be direction of reactance. This is the diagram. So if this is the resistance of the CT, this CT, and then if this is the magnetic reactance, this is the equivalent of the CT. Okay, this is the CT equivalent circuit. So if you draw the equivalent circuit of this, then this CT will be, what will happen? This is a magnetic reactance of the CT and this is a resistance of the CT, right? This is, we can say, RCT, resistance of the CT. Then the CT is coming to the lead is connected. Then there is a lead resistance, RL, right? Lead resistance. Then the relay 87 relay is connected over here. This is a relay is connected. Then on the other side, again the same CT is there. This side also same arrangement. There is a lead resistance RL, and then you have a resistance of the CT, and there is a magnetic reactance of the CT. Then this is connected. This is the equivalent circuit of this. We can say in this way. So this is a RL, RCT, and this is a RL, and this is your magnetic reactance. This is the equivalent. Now, when this CT get saturated, what does it mean? It is not transferring primary current to secondary current. That means its magnetization characteristics is totally lost. That means the magnetization reactance has no magnetization reactance. Magnetization reactance becomes zero. That means this becomes zero. Effectively, we can say it becomes shorted. This is a shorting between these two. This is not present. Okay. Under that condition, if this is shorted, then what will happen? Then the current, this relay is a very low. If this is a relay, so there is a current IR passing through the relay, right? This is IR. Now this IR current, how much IR will be there? That will be dependent between the voltage between this. Now when there is a fault when the CT gets saturated, the total current coming through this, that is the IF fault current is coming. This is the CT. Suppose this is CT saturated during fault. So at that time current is following a fault current. Only this fault current is not passing through this, but it is passing through this. Due to the fault current between these two terminal, that means across the relay terminal, there will be, this is the current IF flowing through this impedance. So there will be a voltage drop in this. How much voltage drop will be there? That voltage drop VF, if we say the voltage drop equal to VF, then VF equals to IF into RCT plus RL. This is the voltage drop. So if this is the voltage drop, this voltage drop will be across the relay, this across the relay terminal. So due to this voltage drop, relay will also follow the current. If the same voltage drop over here, so if this is the Thevenin equivalent voltage, you see VF across this terminal, how much current flowing through the relay? You can say relay current equals to how much? That equal to VF by this relay resistance. We can say this is the relay current VF by RR. Or otherwise, if you want to write this in terms of total current, the relay current, this can also be write as these are two parallel paths. Now when this is coming over here, this RL plus RCT is in parallel to this. So in the parallel path relay current, that can also written as total current, that is IF into opposite path resistance, means RCT plus RL divided by how much? Divided by total resistance RCT, that is the relay resistance RR plus RCT plus RL. That is the equation for the relay current. Relay current we can find out two way. From the voltage drop across the relay, if the VF, then the relay current will be voltage drop divided by relay resistance. That will be the current through the relay. And same current, if the total fault current is IF flowing through this, out of this fault current, how much current passing through this? As this current will be this current IR. As this is a short circuit path, most of the current will going through this. We can also, by slightly compromise, we can write this IR also in terms of fault current, because when I coming to IR, there are two paths over here. At this point, there is a resistance. This is a relay resistance RR, and then there is another resistance here, that is a RL resistance and RCT, and the voltage between these two is VF, and the total current, if I say IF, and there is a small portion of current going through IR, because this is a shorted path. So in that case, we know the parallel theorem. How much current will be? This current through this path equals to total current into opposite path resistance, that means RL plus RC divided by total resistance, that is RR plus RL plus RCT, that is I have written over there. This is the IR current, this IR. So from this equation, you can see, now you see this BA, what we have written before we did the bias factor, we wrote the bias factor, right? So bias factor B equals to what we wrote? B equals to bias factor equal to what we have written over there. If you would see this current, the relay current IR equals to how much? That equal to B into, considering setting current less, B into IF. Here I can write RCT plus RL by RR plus RCT plus RL. This is equal to IR per IF, right? That equal to B, because we have sent B equal to IR by IF equal to B. So if this is the case, then you see this bias factor is dependent on as you increase the resistance, automatically bias will be reducing. That means it will let relay current. Now it will be less. It will be bias factor as you increase the relay resistance, because relay resistance depend on the relay path. We have shown the relay path. This is the relay path. Relay is connected over here. That is RR. So relay resistance also a factor of the B. So if you want to increase the B, you have to reduce the relay resistance, and if you reduce the B, you have to increase the relay resistance. So this is B is also dependent. So bias factor is not depending on the current; it is dependent on the relay resistance or relay path resistance. Okay, and relay current, you can see from here, the relay current, how much current, operating current of the relay, this is IR. Operating current of the relay depending on this is operating current of the relay, that is depending on this factor, right? IF into this. Now here you see the fault current, as we increase the fault current, automatically relay current will increase. That is we have seen from the characteristics. Also you can say if you increase the relay current, if you increase the relay resistance, then advantage of that, as you increase the relay resistance, relay current will be, operating current will be reduced. So by increasing the relay resistance, the operating current we can reduce in the relay. So that's why if you include some resistance in the relay, then the current in this relay will be less, operating current will be less, that it become a high impedance route. So high impedance relay, actually how it is working, we are including additional resistance in the relay to make it high impedance, so that spill current will be reduced. The current amount of, due to CT mismatch, the spill current, the current passing through the relay will be reduced. That is the principle of the high impedance relay. So from this it is clear, the bias will be depending on the how much by including the bias factor we can increase the stability of the relay, and by including resistance in the relay circuit, by increasing the relay resistance, what we can do, the operating current requirement can be reduced. That means relay path can be made when out of the total current, this IR is a part of the total current. So we have a two parallel path. We have seen over here, this is a relay and this is another path. Okay, under CT saturation, if the total current is IF, the relay current can be made less and less, and most of the current will pass through the CT. If we make the relay path is more impedance, if we increase the RR, then the current through the relay path will be reduced, and that means most of the fault current under mismatch condition it will pass through this. So that is the purpose of this. So to do this thing, we have to increase the impedance of the relay path. So how we do that? We can add some additional resistance. So that resistance, when we do in the low impedance circuit also, to make a better stability, we can include some stabilizing resistance. We call it stabilizing resistance, which will stabilize this operation, or give a stability of the operation. That is, on this route we put some additional resistance, and then this relay will be connected over here on this path, and then this is your CT route. Okay, this is the CT route. So this resistance we call stabilizing resistance. By including the stabilizing resistance, we can get the more stability in the case of low impedance circulating relay also. That means this RR we are increasing, so that when we are increasing RR more and more value, so total current which is due to mismatch, what are the total current coming in the circuit, most of the current passing through the saturated CT, and very less current will pass through the relay, so relay will not operate due to mismatch. So this is called stabilizing resistance. Sometime in the low impedance current differential scheme with the bias characteristics, we can include the stabilizing resistance, and we can calculate the stabilizing resistance value from here. When this bias characteristics, we have already calculated this from this equation. We have seen that BF IR by IF equal to B, so B equal to RCT plus RL by RR plus RCT plus RL. Okay, so here if we take this one, then RR, this equals to RCT plus RL, you can take common, then it will be RR equals to 1 is will be 1 by B minus 1. This will be the relay path resistance. So from here, if we subtract the relay resistance, then balance will be this RR equals to relay resistance, that equal to relay internal resistance plus stabilizing resistance. So by increasing the stabilizing resistance, we can get better stability of the relay. Okay, so this is the bias characteristics. Now third part of the relay is a high impedance differential scheme. This high impedance differential scheme is the same principle, it is working on this what I discussed over here. This relay is inherently high impedance. We are adding a stabilizing resistor from outside, but this relay has inbuilt high stabilizing resistance included inside the relay. So relay has itself a high impedance, and when the relay has a high impedance, then what is happening? Then this relay will not, you see how it is happening. Suppose all the CT is connected over here. This is the various CT is connected, right? This is the, suppose I would say S1, S2, this is ultimately a common path. Then relay is connected over here. Okay, if this relay has a high impedance, that means we can replace the relay like this. This is a high impedance. Due to the high impedance, very less current will flow through this. Okay, very less current will flow through this. That means then the relay operation we can make, instead of current circulation, we can make this relay voltage measuring unit. As the current will be, if we increase the impedance in such a value, very minor current, ammeter and voltmeter difference is, ammeter draw the high current is a shunt path, and voltmeter does not draw any current because it is a high resistance. Voltmeter is a high impedance path. So when any equipment, any measuring unit, you make a high impedance, then it becomes voltage measuring equipment. It will not act as a current measuring equipment. But the moment the measuring equipment has a low impedance, it is act as a current measuring equipment. But the measuring element, it has a high impedance, then it acts as a voltage measuring element. So if we can increase the impedance of this relay high value, then it will draw very less current, and then the equipment will be acting as a voltage measuring equipment. So when this relay acting as a high impedance relay, when you use in the circuit, then it acts as a voltage measuring unit, and this relay acts as a voltage based on the voltage available on the relay. So in the case of CT saturation, now when this relay acting as a voltage measuring relay, then the setting of the relay will be given in terms of the voltage. So how we do the voltage? We do the stability of the relay in such a way, during completely CT mismatch or CT saturation, the amount of voltage developed across the relay setting will be more than that voltage. Then under CT saturation condition, the voltage arrived across the relay terminal, relay will not operate, because now the relay is a voltage measuring element. The voltage measuring element we have seen in previously, how much voltage VF under fault condition, that is called IF into RL plus RCT. That is the voltage developed, that is your RL lead resistance plus CT resistance, and this is the fault current, this is the voltage developed across the relay. So if this is the maximum voltage developed in the relay during, because this is we have got when the CT secondary is saturated. So this is the case when this CT magnetizing resistance we shorted, we connect like this, and relay is connected over here. That is the consideration of this calculation. If this is the case, then this VF, this voltage across the relay, this is the maximum voltage can come during your CT saturation. That is the abnormal condition when the system is healthy, but due to outside fault, the CT getting saturated or CT mismatch under any healthy condition, but due to CT mismatch or any external fault, this is the maximum voltage can come to the relay. So relay will be setting VS, that equal to setting value of the relay will be VF into this value, VF into VF, that equal to IF into RL plus RCT, real resistance of the CT resistance plus CT lead resistance. Once we calculate this value, that will be the relay setting. Then during fault condition, the voltage will be more than this, then the relay operate. But any healthy condition, when the fault is not there, if there is any CT mismatch, anything, under any condition, this relay will not operate, because we have considered the worst scenario here. CT completely 100% CT saturated. But normal condition, CT will not be 100% saturated. So some reactance will be always present there. But we have considered extreme conditions. So that is the maximum voltage can come during healthy condition of this system, but due to CT mismatch or CT saturation, based on that, if we use this impedance relay, then this could be protected. This impedance relay, how it is made? This impedance relay actually different manufacturer, different type. So one of the type is your, this is a DC type. This relay is a DC type relay. So this relay we connect through a reactance and a capacitor. Then we put if it is a three-phase relay, then we put a three-phase like this way. Three-phase bridge circuit we provide. This is the bridge, and we connect the relay over here. This is the relay DC. It is a DC relay, and this three-phase voltage giving over here from the 3CD. Okay. So this relay will be connected over here. Okay, and then it is going. That is 87 relay. Now this is a high impedance relay. This is a high impedance voltage balance relay, high impedance voltage balance relay, this type of relay. This relay will be operating by this it is a DC relay, and this is one of the manufacturer like this, and this will be connected over here. Okay, now here this relay, why high impedance relay make this way? This is first of all high impedance relay, so it will not in a abnormal unbalanced condition of the CT mismatch, anything, very less current will go through this. That is number one. And this during fault condition, what is happening? During fault, we have already discussed, the fault is asymmetrical. When during fault condition, the current flowing through the system is an unsymmetrical current. So the unsymmetrical current contain DC component as well as various harmonics. So these harmonics sometimes maloperate the relay. To stop the harmonics, this RC filter is used. so LC filter. So the L will be stop all the high harmonics, only it is tuned to the principal harmonic, the fundamental frequency. So only the fundamental frequency current will pass through this, 50 Hz current will pass through this, all other will be stopped. And if the DC component in the asymmetrical fault current will be stopped by this capacitor. So this relay will be actually, it will not responsive, or it will not be given any response to the any other frequency current or DC component. It will be only reacted with a 50 Hz supply. So this is another part of the relay. So this is called high impedance differential scheme or high impedance voltage balance scheme, because this relay working as a voltage measuring equipment, because very low current is passing through this relay. Okay, this is and what do we do in parallel to the relay, because sometimes in the system overvoltage can come. To avoid the overvoltage across this relay, we put on metro cell non-linear resistance. You know non-linear resistance, this is a non-linear resistance. So what is happening over here, as the voltage increases, the resistance value decreases. So when there is a high voltage come across the relay terminal to damage, so without damaging the relay, the high voltage pass through this metro cell. It is called metro cell resistance. It is actually non-metro cell. This is a metro cell resistor. It is a non-linear resistor. Non-linear resistor. This resistor advantage is, as the fault current increases, as the voltage increases, resistance decreases. So when high voltage come over here, instead of passing through this, it will go through this and it will be grounded. Okay. This is a high impedance scheme. Now all these schemes, so these three different type of relay now we have seen in the differential scheme. Conventional differential scheme where there is no bias, only the pickup setting is there. That is one. Second is a bias differential, and this is a high impedance. Bias differential, high impedance differential difference is, bias differential there is no, with the relay it is a low impedance relay, so it will draw the current, it will work on the current principle. But high impedance relay will be working on the voltage principle, because due to high impedance of the relay path will not draw any current, very minor current will be drawing, so and it will be acting on the as a voltage measuring element. That's why it is called high impedance voltage relay. And that is the best relay, because it is not susceptible to the harmonics, it is not susceptible to the DC component, and it is not susceptible to the CT saturation, because it is working on the voltage setting, not the current setting. Okay. Now we will discuss another couple of points on this when we are using any of the differential scheme. What the scheme we have said, we are on the first day we said differential scheme for the critical and high voltage switch gear. Differential protection always be backup. There will be two, one main protection, one will be main protection. For each zone there will be, it is for each zone. There are 3 zone or 2 zone will be there. In case of double busbar arrangement, it could be 3 zone. In case of bus section, it will be 2 zone. So each zone, it has a main protection 1, then main protection 2 or backup protection. Main protection 1, main protection 2, or it is called backup protection. Or sometimes this is called check feature or check protection. Check feature. So any protection when we are providing for the bus differential, that is differential protection we are providing, always main protection will be there, and then there will be second protection will be there, and that protection we sometimes call the check feature, but check protection will be there. So these two protection will be completely independent, means for each protection, for each feeder, CT will be different. This main protection has a one set of CT, check feature on main protection 2 or backup protection, it has a different CT, and this main protection will be working in one principle, checkup protection will be, or check feature or backup protection will be working in another principle. For 15, all this differential scheme should have this double arrangement. Third arrangement, in case of indoor switchgear, this is fine because CT wiring will limited within the panel. But when the switchyard is outdoor switchyard, that was 636 kV, 132 kV, 220 kV switchyard, which is all the CT, PT, breaker, everything mounted outdoor. So in that case, bunch of wires will be coming. CT wires will be coming, because all the CT are located in the outdoor switchyard. So all the CT when coming to the protection panel, it come with the law over the root. So we do not wire in that way. What do we do? On the field itself, we put a big marshalling kiosk or junction box where we make a CT wiring. We put a busbar inside the marshalling box, and all the CT as per phase connection, we do connection inside this. And from there, we bring a cable, single cable to connect to the relay. That is the normal way you do this. Now, this CT, during bringing the wire, any of the wire can be loose, any of the wire can be open. So CT wire can be open. If the CT wire is get open, then automatically this system will be unbalanced, then the relay will be operating. So we have to monitor the CT wire has not been opened, so, or CT bus wire is not opened, then monitoring also arrangement also required. This third arrangement is a CT monitoring arrangement. Monitoring arrangement should be present. Monitoring arrangement to CT to be monitored. So in case of any CT wire is open, immediately that there will be some monitoring arrangement is required. That is the third point. Another point is this, this issue is that suppose, and in this case when the CT wire is open, immediately what will happen? Then immediately what will this protection? Immediately protection will be operating. No. So we have to prevent the protection of the operating. So when this CT wiring relay, CT wire opening relay will operate, then immediately protection to be bypassed. That means the protection should be protection of the CT secondary side should be short circuited, so that the protection relay will not get any signal or the protection is blocked. That is another point. Another point is when we are putting the CT for the zone, we need to, we have last day we draw only one typical, but that will be copied for the multiple zone. So each zone, whether the protection is operating which zone, we have to identify. Any of the zone maybe protection is out, that also we have to identify. So for that reason we have a selector switch. The selector switch will select whether it will be zone selector switch. The protection is zone 1, zone 2. Each zone there is a contact. So that the zone selection switch should be required to identify any problem with the particular zone protection or not. That is also to be included. Considering all these things, I am drawing one simple diagram, one AC diagram and another DC diagram to illustrate this wiring, how we do it, how the DC or AC wiring and DC wiring. We are coming for AC wiring, but I will not draw more feeder. In that case, it will be very complicated. Suppose this is I am drawing only bus section like this, okay? And suppose there is a 2 feeder over here, okay? And 2 feeder over here. So I am taking only the one section. So there will be CT over here. Suppose this is a one section. Okay, it is a bus zone 1. It is a zone Z1. Okay, so now here, how we do this? Now here, this is a main protection. Okay, so there will be another CT for the check feature or backup protection, or check feature, you can say CH, check feature. Similarly, here also there will be 2 CT. Everywhere there will be 2 CT. 1 CT for the main protection. Here also there will be 2 CT. 1 CT, but in the case of busbar, bus coupler, we don't need this check feature. Only incoming and outgoing feeder, we generally need the check feature CT. So here only main CT will be there. So now when we go for the relay, each protection has a one separate relay. So now here we can do one thing. I am drawing a busbar CT bus. Suppose this is the CT bus for the main protection. This is a bus, B bus, C bus, and this is neutral bus. So what you do, this CT, this is it is suppose B phase, huh? So there will be A phase over here and there will be C phase over here. That will be main protection. Now in this case, these will be connected neutral, and this CT and this CT. All this CT will be coming to the bus. Suppose this is a phase CT. So we can take from here. A phase CT will be connected over here. This B phase CT will be connected over here. C phase CT will be connected over here. That is the main protection one. And then here, similarly, this bus coupler here also, this is your S1, current is coming this way, this is S1, here also 3 CT. So these will be shorted, S2 will be shorted, and S1 will be coming, A1, A phase is here, B phase over here, C phase over here, okay, and neutral will be connected over here. This is this CT. Similarly, this CT for the outgoing feeder, what we said, the current is going this way, this is S1 and this is S2. Now in this case, S2 will be connected, all S1 will be shorted. This S1 will be shorted and S2 will be coming to the A bus for all this CT. This is B bus and this is C bus, right? And this neutral will be coming to the neutral bus. So you see all the outgoing, similarly these outgoing also connected this way. This is a 3 CT. So this is these are shorted. It is coming to the neutral, and this CT will be coming. One is coming over here. Second is coming B phase, and this is your C phase. So these are the CT connected. Now the relay will be connected where A phase relay. This is the neutral. So A phase relay will be connected between, this is A phase. The A phase relay will be connected between A phase and neutral. B phase CT will be connected between B phase and neutral, and C phase CT will be connected between C phase and neutral. These are the 3, 87 B Z1, 87 bus differential for zone 1 protection. Okay, this will be CT wiring. Now here we have to do one thing. When we are connecting this relay from here, so we said that now similarly this is one zone. Similarly, the second zone, the check relay, that also there will be ABC3 section, ABCN. Here is the same way as we did for the other relay. Here also there will be 3 set of CT. This is the neutral. The neutral will be coming to the N bus, and then this CT will be coming to the A phase, will be connected to A phase, B phase will be connected to B phase, and C phase will be connected to C phase. Similarly, here the outgoing also 3 set of CT over here. This CT neutral will be here grounded. So this neutral will be coming to the neutral bus, and this phase CT, if you draw over here, it will come over here, and then one will be connected over here. The second one will be connected over here, third one will be connected over here. Similarly, these will be also connected. Then here also we have to connect another set of relay. So from the A phase, this A phase relay will be here, and this connected between the neutral, and this B phase will be connected over here with the neutral, and C phase will be connected over here with the neutral, right? This will be the C and this will be neutral. These are the 3 check relay. 87, it is 87 check. So these are the 2 operation. Now this CT, we said another thing, that this CT secondary wiring which you do in the field, these wires are all in the field, this is in the busbar. If this CT get open, then what will we have to bypass the relay? Then how will show this thing? How will bypass this relay? Now you see each phase, this is a A phase, this is a B phase, this is C phase. The A phase relay is connected over here, B phase relay is connected over here, C phase relay connected over here, okay? And this is going to neutral. This is A phase, this is a B phase, and this is a C phase, right? This way we have done. Now here, what do we do? This neutral is coming from here, okay? So we put a contact over here. From here, we put a contact over here in this way. If we connect a contact in this way, this is a contact. Suppose we put a relay for CT open circuit. How will happen? This ABC coming from here, and the neutral is coming this, right? Neutral. If we put a unbalanced relay, you know there is a current here. The current is coming from this. If any of the phase CT wire get opened for a particular feeder, then automatically this current going to the relay will be imbalanced. So if we put a 47 relay, current imbalance relay over here, or 90, you can say 95, you can say, so we are putting supervision relay. So if you connect this 3-phase current over here and neutral, the moment there is a CT wire will get open, immediately there will be imbalance in ABC, and immediately this relay will operate. And if this relay contact is connected over here, this is the relay contact 95, then what will happen? The moment relay operate, immediately this relay will bypass, immediately CT supply will be coming through this to the neutral. It will be bypassed through this, so the relay will not be responding to this. So the moment CT secondary wire get open, immediately this imbalance relay which is connected between the ABC, suppose this is ABC phase, here will connect the 95 relay across A, B, C will come over here, it is imbalance relay. The moment imbalance relay picked up, the relay contact will be connected in parallel to the relay, so relay will be bypassed and current will not go through the relay will not sense, okay? This is another CT wiring, and this is the 2 relay 87C and this one, okay? And this is the CT AC wiring. Now if you go to the DC wiring, then how we will do this? We will do the DC wiring the same way. We have discussed that the DC wiring. Now this DC wiring we can do, suppose this is positive and this is a negative, okay? So this is a bus, we have a fuse over here, okay? And then this is a negative side, this is a fuse, okay? Now this relay, all this relay we need a DC power supply maybe, so we can put all this relay, we can connect in parallel one by one. Whatever that, suppose it is 87B1, 87BZ1, then it is 87Z check, then we have a 8795 relay, that is a CT wiring relay. All this relay needs a DC supply, so we will connect over here and it is going to the DC. That is a relay power supply. Then what we will do? When this relay operates, suppose 80Z1, ZB1 is operating, okay, this is, you can put a fuse over here. Suppose this is a 87B1, 87BZ1. This relay has operated. When this relay is operated, then what will happen? It will operate a lockout relay, right? We have said already it will operate a lockout relay. So this is a 1 zone. Similarly, for the other zone, we have shown the bus coupler, we have a 2 zone over here as per our this single line. So this is a 1 zone and this is another zone. So this is a zone 1 and this is zone 2. So this is for 1 zone. Similarly, zone 2 also will have a similar relay, similar set of relay will be connected over here for zone 2, okay? So this is a Z1B1. Similarly, there will be B, this is a 87B, zone 2 relay also will be there, right? These two relay will come to a lockout relay. We have said 86, this is a 86 lockout relay, B1, 86B Z1, and this is 86. Each zone has a separate lockout relay, 86B Z2. These two relay will come output contact. So when this differential relay will work, 87 B1, then 86 B1 Z will be operating. When second zone relay operating, second zone lockout relay operating, then it will go to the check relay, because we have seen another, because differential bus differential scheme always this main 1, main 2, when both the protection operated, then only the bus differential relay should operate. In that case, only the lockout relay operate. So this is a 87 check relay, okay? Because 87 check relay, you have to keep in mind, 87 check relay is not the zone dependent. It is a common for entire zone, only one check facility. Backup protection only for entire zone, only one protection, is not the separate. So in that case, in the case of backup protection or check feature, we need not to give a two separate protection. Main protection will be always, each zone has a separate main protection, but check protection will be common for entire system. So this is one. So this will come to the, suppose this is a negative bus, so it will be through the fuse, it is connected to the negative. So what will happen? The moment zone 1 differential relay operated, immediately, and if both 86 backup protection and the main protection zone 1 operated, then immediately this contact will be NC, then 86 B1 operated, then a lockout relay is operated. And then if the zone 2 is operated, then this is operating it way. And both operated means both will be operated, both zone 1 lockout relay operated, zone 2 lockout relay operated. When lockout relay operated, then what will happen? Immediately, this lockout relay will trip all the breakers on that particular bus section. The bus section for which this busbar differential operated, we have already drawn like this. This is your switchgear. We have drawn only two incomer like this. Suppose this is a busbar 1, bus section 1. The moment 86BZ1, this relay picked up. Suppose this relay picked up means we understand check features has worked and this is also worked. Immediately this breaker, this breaker, this breaker, this breaker, all breaker will be tripped. How we will trip? We have drawn that day. Similarly, here is a DC. This is a DC supply coming. This is a 86BZ1 contact, and this is going to the breaker trip point for each breaker. So this 86B1 relay, this relay may be multiple contacts. So there are how many feeders? There are total. In this case, there are 4 feeders. So it have a 4 NO contact for trip the 4 breaker. And then again, this also NC contact of 86BZ1 that will be connected to the breaker close coil. We have seen that day when the lockout relay operated, then the operator cannot close the breaker till this relay is getting reset. All these relay are the hand plug type hand reset relay. So all this auxiliary contact, in this case we need a 4 NO contact, 4 NC contact. We have maybe this 86B1 relay will be ordering 8 contact, 8 NO, 8 NC contact. Okay, so this is the DC scheme. Similarly, 80BZ2, for the Z2 also the same way. When this relay operating, then corresponding this section, other section of the breaker will be operating and closing. Then it will be giving what is the other things required. This is for the operation. Then similarly, the 95 relay, who is the CT secondary wiring, that relay when this will be operating, we need an indication also for that. So now this is your tripping and closing part. Now for indication part, what we will do? Same circuit below this. I am deleting this part. It will be coming below this. For indication, what we will do? This is a fuse over here. There is a separate fuse indication circuit. We will put 86BZ1. So this will be one contact. One indication lamp will be here. That means we understand bus 1 protection operated. Similarly, it will be another contact is 86BZ2. There will be another indication. That will be show the second zone operated. Now here we can put another indication lamp for 95. That is the CT wiring. If the CT wiring opening, immediately it will give indication the CT wire has opened. Okay. This is a zone 1 operation. It is a zone 2 operated. It is a CT opening, secondary CT wiring open. That indication will be coming over here. Okay. So then we can put another thing. This this zone 1, zone 2 selection. For any unfortunate reason, if any of these guys, the zone 1 selection switch skip out. So in that case, we can put a contact over here. Suppose this is a zone 1 switch. Yeah? This contact is like this way. We draw this way. This is a light. So it is a in. And if it is out, then this will be out position. It is a in position, this is out position. When it is in out, it will give another, suppose this is out means this will be red color indication lamp, this is a red color and this is a green color. So when the this busbar zone protection busbar system is inside, its switch has not busbar as a zone selection as a switch. If that zone selection controls, it is a control selector switch. If the zone selector switch is in, then it will be green color. That means it is a secured condition. But if somebody by mistake, if the switch they put in out position, then the busbar protection will be out of circuit. Immediately it will give a red color. That indication also we can get from here. Then at the end, we can check entire bus wire is connected or not. The bus wire is not loosened. In that case, we can put an indication lamp over here. So it will monitor the continuity of the bus wire. Okay. In addition to this, for a busbar protection, zone 1, zone 2 protection, we take a alarm also. It is not only the indication, we take when the busbar protection operated means I said already, it is a total process plant will be shut down. In the case of busbar fault, entire feeder, all the feeder will be off on that bus section. So there is a huge process plant will be off. So it needs a siren. So how they do it? So they do in addition to this indication, what they do, they put another relay, they put a supervision relay. Suppose this is 86B1, okay, and then it is your 86B2, okay. When 86B1, B2 operate means both the 86B1, 86B2 cannot operate without main protection check pressure, both are operated, okay. Then it will go through another relay. Suppose it is a supervision relay 74, it will go over here. This 74 relay contact, one contact we put for indication. So it will operate, it will indicate that the busbar protection operated, and then on the another contact we can put a hooter. We can put a hooter over here, yeah. We can put a hooter. The hooter will be siren that the busbar protection. When any of these operated or both operated, immediately 74 will be operating. When the 74 operated, this is 74 contact. Indication lamp will be there. It will show busbar operated. And then we have previously separation. Busbar is separate protection is there. Separate indication for bus 1, bus 2 is there. Here we understand bus protection is operated and it will give a siren through this contact. This is another 74 contact. It will give the siren. So this way we can monitor this, and this scheme is a common for all this feature, that is a current differential, bias current differential and high impedance differential. For all these three schemes, this requirement is constant. So this is a common diagram I draw for all this. So if it is a more number of busbars are coming, then the isolated interlock will be also required. So that case to case we have to analyze in busbar protection, and we are discussing just a basic way how we can do this. What are the basic features required in the busbar differential protection? And the last point we will discuss now about the CT requirement. As we said that the busbar protection CT is very important. Location we have already said. Now some of the basic feature of the CT is required. This CT will be all the CT in the busbar protection. Though the feeder rating may be different, but all the CT shall be same ratio. In the busbar differential protection, we should not use any auxiliary CT. Okay, CT ratio of the CT, all the CT will be same ratio. That is one of the basic requirement. Maybe feeder is 630 ampere, incomer is 2000 ampere. Incomer CT is 2000 by 5. Outgoing feeder 630, we generally put 630 by 5. But in case of differential protection CT will be 2000 by 5 for the 630 ampere breaker also. So all the CT will be identical ratio. That is number one. Number two, this CT burden will be at least 50% extra burden should be there on the CT. CT burden will be high burden with respect to the requirement. Burden at least 50% margin should be there. Knee point voltage of the CT. At least 2 times we calculated, we say that at least 2 times of your normal magnetization on the peak point. Peak point of the CT, it will be knee point voltage of the at least 2 times of the V. Okay, that normal operating voltage, whatever the voltage it comes, 2 times of that will be the knee point voltage. This last point is the leakage resistance of this CT will be very, very less, because the leakage resistance is causing the saturation. So leakage resistance of the CT shall be made less. How we can make the leakage reactance of the CT will be very, very less. How we can make that thing? If we make a CT core is a toroidal type core, and over the core if the winding is distributed, then CT will be very, very low leakage reactance. So what we have to do, this bus differential CT shall be toroidal core, or it is a bushing type CT with a distributed winding. That will give the best quality of the CT. These are the couple of basic requirements for the CD for the bus differential protection. Okay, so this is all about switchgear protection. So we have covered switchgear protection, frame arch protection we have discussed, and then switchgear income protection we have discussed, outgoing feeders protection we have discussed, and busbar protection also we have discussed in the 4 different way. And based on this thing, so busbar, these are the overall about the switchgear protection. So I am closing part 3 over here, and as well as I am closing the switchgear protection. And thank you very much indeed. And next session 12 will be continuing with the distance protection and the transmission line protection. Please keep it up with me so that we can continue this protection session. Thank you very much.